Start, Dan.
Okay, thank you very much. So welcome back, everybody. This is the third lecture on gravitational wave backgrounds. And we are gonna continue where we left it yesterday. If you remember, we were missing one fourth definition of gravitational waves. This is gonna be the most generic approach now, based on perturbation theory. And it consists in considering a general background metric, now with bar, and some perturbation on top of it. And the first problem we notice is there is a big difference compared to previous approaches, because now the background also depends locally on space-time coordinates. So there is a problem of separating what is background and what is perturbation. No? If I make now a infinitesimal diffeomorphisms, I'm gonna mix them both, and hence we have a problem in that sense. So the solution actually comes from thinking about the fact that just separating perturbatively in terms of amplitude is not enough. This is a more subtle problem. And what we really need is, on top of the perturbative separation of amplitude of perturbation much smaller than background, we also need a separation of scales. What do I mean by this? We're going to consider that our background has some length dependence or frequency dependence. If we are in the frequency domain, doesn't matter. And the perturbation has a much shorter wavelength. So the characteristic length scale of the perturbation is much shorter than the background length scale. Or in terms of frequency, the perturbation has a much higher frequency profile. And what we are going to do, having this in mind, is we are going to expand our Einstein equations, which we write again in terms of the Ricci tensor equal to the trace reverse energy momentum tensor. We expand first the background Ricci tensor, the total Ricci tensor. We know how to do it because we've been doing it yesterday for Friedman, Lemaitre, Robertson, Walker metric. This wouldn't be any different, just you have to do the calculation and find the functional form, which of course is a bit more cumbersome because yesterday we were using the advantage of having a conformal transformation with respect to flat space. We don't have that situation now. But still you can proceed straightforward, as lengthy as it is, this calculation. And then we can think of the following. So the total Ricci tensor is gonna be given by the background plus a first order perturbation plus a second order expansion in the perturbation. But we can think of this second order as having some low frequency part. If you want, it's going to be a superposition of a low frequency part and a high frequency part. So obviously, when I balance the background with the low frequency part of the energy momentum tensor, the reduced, the trace reverse energy momentum tensor, sorry, I can still balance also the low frequency part here. There's going to be then a high frequency part, which is what you naturally get from the linear order expansion part. No, because this is linear in the perturbation, and perturbation by definition are high frequency. Then we are going to assume there is a high frequency part from the bilinear terms in the second order expanded part, and we are going to assume there is a high frequency part in the energy momentum tensor. Let's focus first on the low frequency domain or long length scale. Now, remember that this second order expansion means that here I have a functional form depending quadratically on the metric perturbations. No, so here is the question we want to ask ourselves. Imagine I have a general tensor. How do I, which is quadratic in some quantity? That's the point here. No, how do I filter out? So how do I eliminate the high frequency part and I maintain only the low frequency part? And actually, there is a natural solution for this. You do a spatial average over the expressions you have, or let it be a time average if we are in the frequency domain. Okay, I'm going to exchange space and time in that sense. So essentially, the fact that we write the Einstein equations perturbatively and separating scales, especially this second point, already forces us, in order to make a consistent equation, to take this spatial average. And this is still a subtle point, but it's a physical motivation for doing this spatial average that we were introducing yesterday. As you see, let me go back here. Imagine this guy were to be high frequency, it wouldn't make sense to balance it in the same equation with this background part and with this low frequency part. We need the low frequency part, and this comes naturally precisely from doing a volume average. And of course, at what scale do I do this volume average? It doesn't really matter. Okay, this is like a renormalization theory. When you choose your renormalization scale, you don't want your observables to depend on that scale. So essentially, you do a volume average over a volume sufficiently large compared to the wavelengths of your perturbations, and then it's not going to matter at what scale you are fixing that volume. That's the idea. And now, if I have these volume averages here, just by inspection of this equation, immediately we can identify that from this second order volume average guy, we can define an energy momentum tensor, which is the trace reverse version of this energy momentum tensor to second order, of this Ricci tensor to second order here. No, because the Ricci tensor is typically equal to the trace reverse energy momentum tensor, like you have here. So we are going to identify this as the trace reverse of the energy momentum tensor that we are going to associate to gravitational waves. If you want, we can write all of this in this other manner after we make this definition. Sorry, at the background level, the low frequency part of the energy momentum tensor, the trace reverse, is the background energy momentum tensor by construction, as we do, for instance, in Bbn Limit, Robertson-Walker. So what we have here now, what we are learning is that the background Ricci tensor is sourced by the background energy momentum tensor. For instance, in the case of an expanding background, that would be the background fluids that dictate the expansion of the universe, whatever these are, or combination of various. And then on top, there is another energy momentum tensor, a trace reverse energy momentum tensor, which actually comes only from the fluctuations of the field itself. So we are seeing how gravity gravitates, how this second order guy is telling how to affect the actual background space-time curvature. We can actually compute in detail, in full generality, this second order inside the spatial average, and actually one term survives only from this spatial average. And this is very interesting because immediately I can plug it here and figure out what is the energy momentum tensor of gravitational waves. And essentially this H, sorry, is the same as delta G. The energy momentum tensor, what we conclude is this bilinear of derivatives mu nu with respect to the perturbations, the general perturbations of the metric. And it can be shown, and for this I recommend you, for instance, to look in this volume 1 of Michele Maiore's book on gravitational waves, that only transverse Euler's degrees of freedom contribute making this gauge invariant. Okay, because notice that here I haven't made any choice of gauge, I didn't make any transformation of coordinates, I'm remaining quite general. But if we happen to be, of course, we need this requisite, to be in a background that is invariant under rotations, we can still define the concept of transverse Euler's degrees of freedom, and actually those are the ones that only contribute making gauge invariant this expression. And voila, do you recognize this expression? It's pretty much the expression we derived yesterday, specialized for the Bbn Limit Robertson-Walker background. So essentially, the energy momentum tensor is quadratic in the derivatives of the transverse Euler's degrees of freedom, assuming there is rotational invariance at the background level. And very important, this is inside a spatial average. So the energy density, it's immediately taken from the 0,0 component here, is essentially the same formula that we arrived at yesterday. Okay. So in summary, in full generality, what we did yesterday is just one case of what you can do in full generality in a space-time background that has rotational symmetry. If you don't have this rotational symmetry, then as I was answering to one of the students yesterday in the turn of questions, you may have to follow more than just the transverse Euler's degrees of freedom in whatever the situation in which you are computing the energy production due to gravitational radiation. and only far away from the source, then you can go for sure into a spherically symmetric situation if you are far away, and then define back again your transverse traceless degrees of freedom. Certainly, you can always do that whenever any of those waves arrive here at Earth. Okay, what about the high frequency short scale part, the other side of the equation? So here we are balancing out the first order expansion of the Ricci tensor with the high frequency part of the trace reverse energy momentum tensor and the high frequency part of the second order expansion of the Ricci tensor. Now, by simple dimensional analysis, one can immediately arrive into the easy conclusion that the typical amplitude of this high frequency part of the second order is suppressed compared to the first order by the ratio of the wavelengths of the gravitational waves to the background length scale. For instance, in the case of expanding background, you could plug in here the Hubble scale, the Hubble radius. If it's another situation, you plug whatever scale, but we were based our whole expansion on the fact that the wavelength is much smaller. So this is a number much smaller than 1. Hence, this guy is absolutely negligible compared to the left-hand side. So essentially, what we write is only the left-hand side balanced by the high frequency part of the energy momentum tensor, trace reverse. We can expand we can explicitly write in terms of the metric perturbations, the first order Ricci tensor, and it has this form in terms of covariant derivative with respect to the background metric. And of course, we can define now again the Lorentz gauge with respect to this so-called trace reverse metric perturbation, which now looks like this. And essentially, it's the same story as we were doing initially yesterday. We take this Lorentz gauge, and then we can simplify the equation of motion of the first order from the Ricci tensor into a wave operator where the covariant derivatives are those taken in the background, in the gravitational background. Essentially, what we have derived here again is that if we go to the Lorentz gauge, we see that the dynamics simplify in this manner. But of course, we know that it's only the transverse traceless degrees of freedom that really carries energy. And therefore, you can go just directly to take the transverse traceless degrees of freedom. And when you solve this equation, now you know the degrees of freedom are really those propagating energy. And finally, of course, if we have matter, so essentially we have to plug in here the anisotropic stress. This comes from the high frequency part here. And in particular, for gravitational waves, is the transverse traceless part. Essentially, if you solve this equation in any context in the early universe, then you are going to be solving the same equation we were solving yesterday, which I'm going to repeat in a moment, no? Which is the wave operator in an expanding background sourced by the transverse traceless part of the anisotropic stress. So in summary, we have covered 4 approaches in complex increscendo in complexity, no, in our definitions. But I think it's time we move into the actual sources. And before we just do that, let's gain some perspective again, as we did yesterday. So essentially, we are going to be looking at the expansion history of the universe described by the Friedman Limit Robertson-Walker background metric, considering perturbations on top of that background, which are transverse traceless, because those are identified with the gravitational waves. We know what is the equation of motion, is the one I just wrote in a general background, which we did explicitly yesterday. It's the wave operator in an expanding background with a friction term here with the derivatives, sourced by the transverse stressless part of the anisotropic stress, which is the deviation of the full energy momentum tensor in the universe with respect to the background one. And the situations we're going to be looking at are those whenever scalars, gauge fields, or fermions in the early universe get excited and they develop a non-trivial or a non-negligible transverse stressless part of their anisotropic stresses. And we are going to specialize, as you know, in the very first second of the universe. So essentially, In this lecture today and partially tomorrow, I'm going to cover what I call the second block of topics, where we are going to discuss what are the gravitational waves from inflation and what are the gravitational waves from preheating. Okay, is there any question or doubt related to this fourth approach of definition of gravitational waves? Or maybe you prefer to postpone any discussion in any case for the questions session tomorrow. I'm happy to take any question on this if you want. Otherwise, I'm also happy to discuss about it tomorrow.
I have a very brief question.
Yes.
You mentioned now scalars, vectors, fermions. I was wondering, what about gravitinos?
Yeah, of course. If you had gravitinos, of course, if you have spin, I mean, you know, I was referring to any kind of fields. I put the standard scalar, vector, and fermion. But if you have any other field representation of different spin, of course, that would also emit gravitational waves.
Yeah.
That's right. Yeah.
Okay.
As long as you have a situation where you excite them, you know, in a special manner. Okay, you need to have a non-vanishing transverse traceless part of their energy momentum tensor. Okay.
Thank you.
Thank you. Okay. Any other question, or shall I start with the second block? I take a sip of water while you think about it. I take there are no questions, then let us start with a primer on inflation. So inflation is the leading theoretical framework to explain the early universe. And inflation was formulated or was put forward because the hot Big Bang framework, the framework that we just described in the first lecture on Monday, has its own conceptual inconsistency problems. And in particular, it is inconsistency with causality, the fact that the universe is homogeneous and isotropic at all scales. So inflation is a natural mechanism to provide a solution to that, as we will see. But much more importantly, and the reason why inflation became such an important working framework, is that because it provides the initial conditions for the universe. Understanding by this, it provides a physical mechanism for the primordial perturbations that we see in the universe, in particular the scalar perturbation, scalar curvature perturbation, and we also think it predicts a tensor perturbation spectrum, which we will identify with gravitational waves. Covering this, it's precisely what a typical course on the basics of inflation covers. So I'm gonna try to give you some details about how to work out these aspects of inflation, assuming that some of you may have never seen this in detail. No? So inflation is actually a very simple idea. It's the idea that in the early universe, the expansion of the universe went in an accelerated fashion, blowing up the scale factor at least 60-folds. What does it mean 60-folds? It means that the scale factor during inflation grew at least e to the 60, which in linear scales means 1 centimeter was blown away to at least 10 to the 28 centimeters. The definition, the technical definition of inflation is actually a period of accelerated expansion, which mathematically is actually equivalent to the shrinking of the comoving Hubble radius. So during inflation, essentially, once you establish inflation, say in a small patch initially in the universe, then that patch starts inflating and homogenizes everything inside. And at some moment, you can think of having, let's say, once inflation is fully at work, you have an inverse Hubble scale, comoving Hubble scale, and this inverse comoving Hubble scale is shrinking exponentially until you reach the end of inflation. From then on, this Hubble radius, the comoving Hubble radius in this notation, grows linearly with time until the current horizon today. All right? So in a fraction of a second, we shrink exponentially fast the comoving Hubble radius and then we take 13,700 millions of years to grow until the current horizon. Hence, the minimum demand of inflation is that the starting co-moving Hubble radius is bigger than the current co-moving horizon today. And if we translate that demand in terms of the number of e-folds, so how much exponential growth we demand of the scale factor during inflation, this translates into the requirement that we need at least 60 e-folds. That's where the 60 e-folds come from. So consequences, if you have 60 e-folds, you solve something called the horizon problem, which is a causality problem there is in the standard picture of expansion of the universe in the hot Big Bang picture. Okay, is what I said before. You cannot have the homogeneity of the universe at arbitrary large scales. You need a causal mechanism to produce that, and that's precisely inflation during 60 e-folds. And as a bonus, you also solve another problem, which is that essentially the curvature in the universe, it's essentially vanishing, the global curvature of the universe. Okay? This is not a real problem because it could have been that the universe was flat from the beginning, but it's a fine-tuning problem, which means that if initially at the early universe there was some curvature, that would have blown up and we wouldn't see a flat universe today. Okay? So inflation provides a natural mechanism to solve dynamically the horizon and the curvature problems. How to implement inflation? Well, you can implement it in multiple manners, but certainly since inflation is a phenomena that expands isotropically the space, it's easy to think that a scalar field is responsible for it. And not only it's easy to think that a scalar field is responsible for it, it seems to be trivial actually to cook up potential, to really design, engineer a potential for this scalar field, such that if the potential energy is much larger than kinetic and gradiental energies, you ask yourself what is the equation of a state of such a situation, and you compute it, and approximately is -1, which is what corresponds to a cosmological constant. And a cosmological constant, as we know, in the Friedman equations, gives rise to an exponential expansion. So essentially, how to implement this in different scalar theories? Typically, people demand from your scalar potential the slow roll regime. Physically, a slow roll regime, what it means is that the kinetic energy of your scalar field is much smaller than your total energy of the system. This is the epsilon parameter being much smaller than 1. And also that the acceleration of your field is much smaller than the friction term in the Klein-Gordon equation. This is the condition that sustains inflation for sufficiently long. And turns out that even though it's not needed, it is sufficient to define these epsilon and eta potential parameters in terms of the potential. And if these parameters happen to be much smaller than 1, that's a sufficient condition for the physical epsilon eta slow roll parameters to be much smaller than 1, which is what we want. So you can envisage potentials that verify this condition being smaller than 1. Then this gives you a slow roll. And if epsilon and eta are smaller than 1 sufficiently long, then you get what we call a quasi-de Sitter spacetime. Quasi-de Sitter because it's like a almost de Sitter spacetime, so cosmological constant, but it's quasi because in reality the scalar field is evolving, and at some point we need to end inflation and we are going to break the exponential expansion. Simple paradigmatic example: harmonic oscillator, quadratic potential, free field. Look, I can compute immediately the epsilon v parameter. It tells me that it's inversely proportional to the field amplitude, and for instance, the number of e-folds is quadratic in the amplitude of the field. So from these scales, immediately I see that if the field is of the order of 10 times the reduced Planck mass, the epsilon parameter will be of the order of 10 to minus 2, which is precisely what you want. And the number of e-folds will be of order hundredths, which is of the order of 60 if you want, or more than 60, which is totally fine. Of course, this case of a study is just for academic purposes because this potential is ruled out. But for the sake of explanation, let us look at this kind of potential. A monomial potential does not even need to be quadratic, can be even a different power. And what we learn is that when we put our field at sufficiently high amplitudes, the natural rolling of this field along its potential, it's in a slow roll. You are doing nothing. The only tuning here is that you are setting up the initial condition of your field at this high amplitude. And this is one of the problems of inflation, that inflation is a theory of how to inflate the universe, but now how to start the inflating the universe. Okay, we don't know how those conditions were set up. But if they were, then you naturally, just by rolling, you slow roll, you inflate until you hit a given value where the epsilon eta parameters become order 1 and you stop inflation. So it is actually almost trivial, very easy to envisage, to engineer potentials that do inflationary dynamics. Okay. So in inflationary dynamics, in a slow roll, but in reality, we don't even need a slow roll, but okay, for the sake of the argument, let's say we are in a slow roll, then we finish inflation when the slow roll parameters take order 1, and in between we inflated the universe at least 60-fold in a quasi-de Sitter stage. This makes the universe to look absolutely flat spatially. This is what we've seen with the CMB anisotropies. We also saw this consequence, not in detail, but we mentioned it in the first lecture. The universe is spatially flat, and it solves the causality problem, the big problem of the hot Big Bang cosmology. Is that all? Well, so far I've been describing the background dynamics. Obviously, that's not all. This is not really why inflation is so famous. We really need to consider fluctuations on top of this background dynamics, because as we will see in a moment, inflation is actually a natural generator of primordial fluctuations. And this is really what it gave inflation the entity of a good solution for the early universe. Inflation is a generator of primordial fluctuations. And you may ask yourself, well, but why even I have to consider fluctuations in first place? And the reason is because if we think of this scalar field, our scalar fields in our description field theory, they are quantum. And there is no reason why quantum mechanics wouldn't apply here. So even though we might be in a classical configuration dominated by the large initial amplitude of the field, nothing prevents that field from having quantum fluctuations. Okay? So if we apply quantum mechanics, what we discover immediately is that what we identify with the classical configuration is precisely the expectation value of this quantum fluctuating field. And on top of this vacuum expectation value, we can consider that there are quantum vacuum fluctuations. Now, the expectation value of these fluctuations is vanishing, but the quadratic form expectation value of it is not. So there is a variance. These fluctuations are positive, negative everywhere. They balance out to mean value vanishing in the fluctuations, but there is a variance. There is a typical size of the fluctuations, positive or negative. Okay, let's look at it. But remember that we are not in Minkowski. We are in a curve from the space-time point of view, space. So we are in quasi-de Sitter, which is a space-time curve space. This means that when we do physics here, we need to consider not only the fluctuations of the scalar degree of freedom, the physical field responsible for inflation, but nothing prevents us also from considering fluctuations of the metric perturbations. Not only nothing prevents us, quantum mechanics demands that we consider them. So what we are going to do, it's a decomposition of our total metric as we did yesterday. And we are going to consider on top of the Friedman, Lemaitre, Robertson, Walker, quasi-de Sitter background, a scalar vector tensor decomposition. Okay, here I don't put the full decomposition, but essentially I wrote it here again. This looks in the same fashion as we were doing yesterday in a couple of examples. Now, what's interesting about the expanding background, which I didn't mention yesterday, is that in an expanding universe, the vector perturbations, even if they are created, they decay with the expansion of the universe. And since the expansion is exponential, in the case of inflation, we essentially can forget, because they are exponentially small, exponentially suppressed, any vector perturbations. So essentially during inflation, we only care about the scalar fluctuations and tensor fluctuations. Good, so there are a number of degrees of freedom to follow. typically for scalars in the metric. We know they are not all independent, but in full generality, there are 4 a priori, plus the scalar fluctuation of the field. And then there are tensor degrees of freedom in the metric, which we know will be identified with gravitational waves. If we make a diffeomorphism, general transformation at the infinitesimal level, we know that the scalar parts are not gauge invariant, whereas the tensor is. We learned this yesterday. So essentially, this invites us to build, like we did yesterday in the second case, some functions, some scalars, which are actually gauge invariant. And among them, there is the zeta parameter, which is also very similar to the curvature parameter, which is a gauge invariant measurement of what are the scalar fluctuations produced during inflation. And note the mixing. We are mixing here fluctuations of the scalar field with fluctuations of the scalar type of the metric perturbations. All right. And essentially, in order to make a fully gauge invariant transformation, we need to do this kind of combinations. All right. So you see, that's another reason why, in reality, when we apply quantum mechanics, we should apply to the full scalar sector, if you want. No, in this case, a gauge invariant scalar quantity. So, for instance, we fix the gauge, we fix this E scalar, and we take a slice in the universe where the fluctuations of the field are vanishing. This is like a choice of a special system of coordinates. Then our spatial metric, it's simply given by the curvature perturbation. They are called like that because they are modifying the would-be vanishing curvature otherwise here, and the tensor perturbation. And this is the typical approach people take. So this R, in reality, is the same as this psi here. But since I'm taking E0 and delta phi 0, then I can write curly R, the curvature fluctuation, gauge invariant. So the approach to study inflation consists, or to study inflation as a generator of primordial fluctuations, consists in taking this metric in the way we've written it, even if we are in a particular gauge. Once we figure out what happens to this curly R and to this tensor here, this will be gauge invariant quantities, all right? Because we identify them with such. So we need to plug in this expansion into our action. Our action now contains Hilbert-Einstein term for gravity and the scalar dynamics dictating the inflation of the universe. We know how to do these expansions. We did them in detail yesterday. So the expansion of the action comes in 2 flavors: the background, inflationary dynamics, the 0 order, and 2 terms for the second order on a scalar part and another one on tensor part. The scalar part, this is exact. This is how it looks. It's like kind of harmonic oscillator-ish with the scale factor here and this volume element here. And with the tensors, inside the Hubble radius, this is the second order. Expansion of the action, as we saw yesterday. We also saw yesterday that there can be other terms, but there is a discrepancy in the literature, so we are not going to put them because in any case we are only interested in the very deep inside regime inside the Hubble radius during inflation initially. You will see initially, and then we don't care about those terms at this level of the action. Okay? So, scalar fluctuations. Imagine you are Mukhanov, okay, like 40 years ago, and you look at this second order Lagrangian action, and you say, okay, what can I do with it if I want to quantize this? Well, in order to quantize, you need to do some massage, no? The first clever thing is to go to conformal time, which now, sorry for the change of notation, but so far T now was meaning, cosmic time, and now I'm going to call tau the conformal time. Unfortunately, later on, I'm going to change back to T being conformal time, okay? But I will let you know when that happens. So for the time being, tau is conformal time. And then what Mukhanov realized is that if he defines this new variable V, proportional to the curvature fluctuation through this Z function, where this Z function was the volume element we have here, or some part of this volume element, essentially he can rewrite the action of second order in this fashion. And what is this form? This is a quasi-harmonic oscillator. It has the form of a kinetic, gradiental, and mass term. So harmonic oscillator, like if it was in Minkowski, like if it was in flat space-time, where we know how to quantize things. The difference with a harmonic oscillator, that's why I call it a quasi-harmonic oscillator, is that there is this term, the derivatives of Z. And remember that Z is this combination. So the derivative of Z actually can be computed exactly to first order in slow roll, and is inversely proportional to the time scale square times this dependence on the slow roll parameters. In exactly the sitter, epsilon and eta would be 0, and I would have exactly 3/2. And then I will have here 9/4 minus 1/4. But in quasi de Sitter, which is when you are in a slow roll, space-time is slowly changing, and this is controlled by epsilon and eta. Very good. So we can write down actually the equation of motion is here, and now we can think of quantizing. We do canonical quantization of this field because this is a canonically normalized oscillator as long as this frequency doesn't change very fast. All right. So we do a canonical quantization, and essentially there are, for the mode functions here that multiply the creation and annihilation operators, there are two linearly independent solutions to this equation. This is a second order linear differential equation with a time dependent mass with the time dependence given by this expression. The solutions to such equation corresponds to the Hankel functions. There are two Hankel functions, but we are going to keep only one of them because only one of them give us positive defined eigenvalues of the Hamiltonian, and also at the same time positive defined norm of these mode functions. So essentially, you can build what is exactly your solution to this time-dependent equation based on the fact that at sub-Hubble scales, so deep inside the horizon, the Hubble radius, you demand to have quantum fluctuations a la Minkowski, where the expansion of the universe doesn't matter. And this makes all the sense if you think about it. If you look at this equation, and I look at the behavior of these mode functions deep inside the Hubble radius, this means that k squared is much larger than z prime prime over z. So this equation becomes just oscillator equation with k squared, and you neglect this. And the solution to that is precisely plane waves. Okay, and the choice of the minus here has a physical meaning, because there could be positive, these are called positive defined frequency, and there are negative defined frequency with a plus here. But the physical meaning is that the choice of negative here gives me positive defined Hamiltonian age state and positive defined norm. For the other choice, it would be negative. So we are gonna keep only this, and hence only one Hankel function. That's the idea. This is called the Bunch-Davis vacuum, in case you've never seen it. So essentially, we are taking a physical prescription, which is my fluctuations, my quantum mechanical fluctuations during inflation, deep inside the Hubble radius during the inflationary regime, they look pretty much as normal fluctuations in flat space-time, because they oscillate so fast that they don't see the expansion. And now, still, you know, we have to match the solution of that deep inside quantum vacuum fluctuations in flat space-time with the actual solution to the full equation that has the z prime prime over z frequency term. And that matching is precisely what defines this functional form with the Hankel of type 1. If we undo our change of variables, we can ask ourselves, since these are the mode functions that represent represents, you know, if you want the amplitude of a quantum operator in this linear combination with the creation annihilation operators, we can ask ourselves now what is the expectation value, the quantum mechanical expectation value of our curvature fluctuation, of our quantized curvature fluctuation, for which we just introduce the change of variables here, and we know what is the expectation value of these V's because we know how expectation values over creation and annihilation operators go, and we know the functional form of the mode functions. This is the answer. The expectation value, the spectrum of this guy, is given by these dependents: the Hubble rate, the velocity of the scalar field, and the amplitude of the fluctuations given by this expression. And this is called the scalar power spectrum. Scalar because these are a scalar quantity. We can define a more convenient combination, which is multiplied by k to the 3, the previous power spectrum. And then here comes the amazing thing of inflation. We produce these fluctuations initially at sub-horizon, sub-Hubble radius scales, but since the universe is inflating, it's gonna inflate, it's gonna expand the wavelengths of these guys. And once they become a super Hubble radius, they actually become constant. They do not depend on time anymore, and they take this form. So this is the spectrum predicted by inflation when initial quantum fluctuations at very small scales, much smaller than the Hubble radius, are blown up to cosmological scales due to the expansion of the universe. There is a question in the chat, could be? Isn't this more a correlation function? Depends what you, so there's a question by Emanuele. Isn't this more a correlation function of the scalar perturbations? Well, that depends what you mean by correlation function, okay? I could talk of correlation functions in real space, correlating one variable in one position with another variable in another position. Here I'm correlating, if you want, the Fourier modes of this curvature fluctuation, but due to the statistical homogeneity, this is proportional to a delta of Dirac. So essentially, this is only non-vanishing when the modes are opposite. Or if you want, when this guy is the conjugate of the second guy is the conjugate of the first one. In other words, this is the modulus square of this guy. So hence, I am characterizing the variance, the typical amplitude of the fluctuations of this guy. So it's not a correlation, it's the typical amplitude, and this is called power spectrum, what governs this amplitude. Okay. Let's continue. I could do the same with tensors. So what do you do with tensors? You take your second order expansion in the sub-Hubble limit. You do similar transformations as before, and then you realize you can write your action again in terms of a quasi-harmonic oscillator, where the time-dependent mass term now comes from the scale factor directly. So same procedure as before, we quantize, define the Banks-Davis vacuum, and then we can obtain the power spectrum. And this power spectrum multiplied by k to the 3, again, when you go to the super Hubble radius scales, which you naturally go because of the expansion of the universe, becomes time independent. So essentially, the amplitude of my tensor spectrum, it's now controlled by the Hubble rate here. So let's summarize. Inflation is a natural mechanism to explain the homogeneity and isotropy of the universe, okay, the cosmological principle if you want. But more importantly, it provides a natural mechanism to give fluctuations, primordial fluctuations at those within the universe, in particular the scalar fluctuations. It predicts the spectrum of these fluctuations in terms of the properties of the inflationary spacetime. The Hubble rate during inflation, the velocity of your scalar field responsible for inflation, the inflaton. There can be some scale dependence, which is a power law prediction, with the tilt of this scale dependence depending in this linear manner of the slow roll parameters. And for the tensor perturbation, this is pretty much the same. We predict that there is a small tilt, now given only by the slow roll parameter epsilon, and the amplitude of the fluctuations themselves depends only on the Hubble rate. Okay? So essentially, the picture, the physical picture is during inflation, while the comoving Hubble radius is still large, so very deep inside sub-Hubble, we produce through quantum fluctuations the amplitude of this curvature and tensor modes. eventually the Hubble inverse comoving radius becomes very small, which means these fluctuations exit the Hubble scale, and they freeze actually. When that happens, they become constant, and they remain super Hubble until after inflation, during the standard expansion history, they eventually re-entry. And in that moment, they take some action, okay? With this, I finish, I believe, 45 minutes. I think I nailed it in time. End of my primer on inflation. Maybe we can take a break, and I'm certainly happy to take any question if someone else has a question. I see that Emmanuel is satisfied with the previous question, but happy to elaborate more on that or take other questions.
Rotem, you can just pick up.
So a quick question about these perturbations. How do they work with unitarity? Do we need to break unitarity to get these perturbations?
Why?
It just seems like anytime you introduce like a perturbation, it's kind of irreversible.
I'm not aware of any breaking of unitarity. This is a standard quantum fluctuations, pretty much the same as what you study in chapter 1 of any quantum field theory book. It's just applied to the expanding universe, but I'm not aware of breaking of unitarity.
Okay, thanks.
I mean, it's as weird as it is, quantum mechanics, you know, it produces fluctuations. The funny thing, the physically appealing aspect here is that, contrary to flat space-time, is that here space is blown up exponentially. So as soon as you produce these fluctuations at sub-horizon scales, you stretch their wavelength exponentially, they leave the Hubble radius, and they become like classical fluctuations in that moment. So actually you can demonstrate that their, let's say, occupation number associated to them, it becomes very large, exponentially large. Or if you want, in a more technical level, the Wigner function that measures the distribution in phase space actually becomes very elongated in one direction, which is what signals that a quantum field is becoming classical. So essentially, inflation is nice because it takes out of the initial quantum vacuum at shorter scales and promotes these perturbations to cosmological scales. So welcome back. What we've seen is that inflation generates, thanks to quantum mechanics, the spectrum of primordial perturbations that we have seen in the universe for scalars, and we hope to see for tensors. Now, let's see how these tensors are actually meant to be identified really with a stochastic gravitational wave background. So let's think of the tensors as a quantum field. No, this was the procedure we actually use. Decompose in the standard manner here, no, with the mode functions, creation and annihilation operators, and here I'm back to use T as conformal time. And I'm summing over polarizations, okay, but these are details not relevant. Now, we already have worked out what is the energy density associated to some tensor field. We know that it is the volume average over sufficiently long volumes compared to their wavelength, such that this does not depend on the location, okay, which can be written in this volume integral. And if you Fourier transform each of the guys, essentially you factorize out this guy here, which in the large volume limit is nothing else by a delta of Dirac, or it converges to a delta of Dirac, so you can eliminate one of the K integrations. And in other words, what I'm saying here is that the energy density of gravitational waves, given our master formula, is always given by the integral over some expression in Fourier space. And this expression is what we call the energy density spectrum. We will define it more clearly in a moment, okay? It's what is here. Now, if the formulas we derived 2 days ago and yesterday have to do with volume averaging, well, in the case of inflation, what we really have is a quantum field. So what we can do is to substitute the idea of the volume average by an ensemble average, with the expectation value being the quantum mechanical expectation value. Is the same idea of the ergodic principle, no? So essentially, this means that now I can write these guys in Fourier space, and now I pass the brackets, which is the quantum mechanical expectation value, over their Fourier transforms. And essentially, we can define the expectation value of these Fourier transforms, of the derivatives of the tensor perturbation Fourier transforms, as a power spectrum of these derivatives, which again, it is a power spectrum. Not, remember, because of statistical isotropy, we have this k equal to ks prime, because here I have already the conjugate. So essentially, the energy density of gravitational waves of a stochastic background can be characterized by this function inside. And this function comes from the expectation value of the bilinear in derivatives, and is called the power spectrum of the derivatives. And it characterizes what we call, what I was saying before, the energy density spectrum, logarithmic spectrum. So essentially, the energy density logarithmic spectrum of a stochastic background that is characterized by the expectation value of some of its variable, it's given by the power spectrum, is controlled by the power spectrum of the expectation value of the bilinear in derivatives. Okay, now remember that what happens in inflation is that we excite quantum mechanically the wavelengths here. They become super Hubble radius, so they freeze. They are frozen during cosmological evolution until they re-enter. Once they re-enter, is when they become really waves, and they start propagating as waves, because a constant function is not a wave. Okay, so it only becomes a wave that oscillates and propagates once it has a wavelength smaller than the Hubble scale. So its period of oscillation is shorter than the time scale, Hubble time scale, and hence it starts oscillating. Okay, so at horizon entry, tensors start propagating because the solution to their wave equation stops from being constant and becomes damp oscillators, damp because of the friction term, and oscillators because they were respecting the wave equation. So, for instance, during radiation domination, this tensor guy, this is one of the polarizations, for instance, is going to be a linear combination of these two linearly independent solutions to the differential equation that governs the dynamics of gravitational waves. At horizon reentry, since it is inflation that set up the initial conditions, there is only an amplitude non-vanishing, that from the spectrum of from inflation, and the derivative is zero, because if this guy was constant during super Hubble scales, the velocity is also zero correspondingly. Okay, so at horizon reentry, we can impose that the amplitude is given by the amplitude that was set up during inflation, and the velocity is vanishing. In the moment I fix this determines what are these constants, A and B here. It's given by this simple expression, the amplitude at horizon reentry times the scale factor in that moment. So I can compute what's the expectation value of the bilinear of derivatives. Is, of course, once they behave like this, k squared times the expectation value of the bilinear of amplitudes. And the amplitudes, we know what it is. A and B coefficients are given here. We plug them here. We take this expectation value here. And this is what we get, some scale factor dependence coming from the actual damping of the gravitational waves, and the expectation value of the initial amplitude. And this expectation value is what defines precisely the inflationary tensor spectrum. Whereas here, notice that the scale factor at horizon reentry, we just express it in terms of the redshift. So when every wavelength re-enters the Hubble scale during the post-inflationary expansion, then we are going to develop a bilinear, a spectrum of the velocity of the perturbation, of the tensor perturbation, proportional to the original inflationary tensor spectrum times some redshift dependence. the redshift depends on the moment on horizon crossing, which depends on the wavelength, of course, we are looking at. So putting things together, the power spectrum of the derivatives can be absolutely computed, and hence the energy density spectrum of this background, once it becomes really a background, can be also computed. And as you see, is given by the original inflationary spectrum times some scale dependence, scale factor, times a redshift of the horizon reentry. The redshift of horizon reentry can be absolutely easily computed because it corresponds to the moment, to the horizon, to the moment in the expansion history when a given wavelength becomes equal to the Hubble radius in that moment. Okay, wavelength is k, the inverse of the wavelength is k. So we can express the redshift in terms of k. We plug in this expression here, and it cancels out actually the k square dependence we had, at least for radiation domination. So essentially during radiation domination, what we predict is that every time the tensors cross the Hubble radius and become part of the background, so they start behaving as gravitational waves that oscillate and propagate, they contribute to the energy density spectrum of that background in a scale invariant manner. Why scale invariant? Because we are picking up the scale, the power spectrum from tensor perturbation here, which was quasi-scale invariant. If you remember, there was a small dependence on the tilt on the slow roll. We will comment more on that. And if you redshift, this is for every moment of expansion characterized by the scale factor A, once the mode, the tensor mode, has entered the Hubble radius and became a propagating wave. And if you redshift that, and you ask yourself what is the energy density spectrum today, normalized by the critical energy density, this is what defines this omega parameter. Keep it in mind because we're going to use it a lot, okay? Energy density logarithmic spectrum, normalized by critical energy density. Well, it turns out that all these factors cancel out, and we are left with this dependence of omega radiation degrees of freedom today, which is of the order of 10 to minus 4, 10 to minus 5, times the original spectrum of tensors. So essentially, the gravitational wave normalized energy density spectrum today, it's proportional, at least for the modes that cross during radiation domination, to the inflationary tensor spectrum, just directly like that. And the function that makes the difference, that multiplies the inflationary tensor spectrum here, is what we call the transfer function, which for radiation domination is a scale invariant, is a scale independent, because we cancel out those k dependencies. But for instance, for matter domination, when the modes cross the horizon in the late expansion of the universe after it becomes matter dominated, or later on dark energy, we pick up a scale dependence in the transfer function. I'm not reflecting this transfer function here with a scale dependence, because here I'm talking only about the background from modes crossing during radiation domination. And now what is really relevant is the spectrum today, energy density spectrum, is proportional to inflationary tensor spectrum. And the inflationary tensor spectrum, remember, was proportional to the Hubble rate square, so to the energy scale, which hits one of the questions that I got in the first lecture, if you remember. Why so important second lecture, I don't remember, to detect this background, and how do we know an upper bound on the energy scale of maximum temperature of the universe? This comes from the fact that this background of gravitational waves is proportional to the Hubble scale, hence to the energy scale of inflation. And it has some scale dependence, a small red tilt, red because this is negative, but essentially the slow roll parameter is so small, even from observations, that this is really almost quasi-scale invariant. So in summary, during inflation, on top of the inflationary background, there are fluctuations, quantum fluctuations. If we focus on the transverse Euler's degrees of freedom, which is what we are interested ourselves for gravitational wave backgrounds, we see that quantum mechanics predict a vanishing fluctuating field. The mean value is vanishing, but it has a size, characterized by the variance. And the size is given by the power spectrum, and the power spectrum is proportional to the Hubble rate square, that is the energy density of inflation. So how does it look, this energy density spectrum of gravitational waves today, if we plot it versus frequency. We have all the pieces of information here. This is how it looks. I'm plotting the log of the energy density spectrum of gravitational waves versus frequency. And essentially, to first approximation, it's a straight line. It's a scale invariant spectrum. If we take into account the slow roll correction, the fact that there is this tilt is quasi-scale invariant because it's slightly red tilted, okay, which means it has some small tilt here, as represented by this dashed line. And if we were to think of the spectrum for modes that cross during matter domination, then we would pick up some scale dependence, in particular to K2 minus 2. So the spectrum goes up like this. And this is how today, if we were capable of detecting by direct detection the energy density spectrum of gravitational waves from inflation would look like for a given energy scale, okay? Now, what's relevant about this plot? What's relevant about this plot is that I'm showing you the best case scenario. This is the maximum energy scale we can tolerate from CMB observations. Because from CMB observations, we know that we haven't seen this background of tensor perturbation. So we have put a bound on the energy scale of inflation and hence on the height, on the amplitude of this background. So the problem is that from our point of view, let's say where we are interested in direct detection experiments, this is not observable. Look at LISA here, sensitivity curve. Look at advanced LIGO once it reaches this design sensitivity. So it's orders of magnitude below any of the experiments that is currently working or planned to be working in the next 20 years. I don't put all the experiments, but the situation is the same for them. So very sadly, it's not observable by direct detection experiments, but yet you have heard me talking about the CMB several times. It is hopefully or perhaps observable at the CMB, even if we haven't seen it yet. The reason being is because tensor modes create what we call B modes in the polarization field of the cosmic microwave background, and the B modes are only sensitive to vector and tensor perturbations. And since vector perturbation dies away in the expanding background, it's like the B mode is just like a probe of tensor perturbations. In other words, to this background of tensors. We haven't seen it, we put upper bounds, but there is a plethora of experiments, the so-called, well, the current experiments in development and the stage 4 experiments of CMB that will aim to look for these tensor fluctuations in the CMB in the B mode. Okay? So the search for these B modes at the CMB could be possibly the only chance, I should say chance here, to detect inflationary tensors, or not. Now I throw you a question to the audience. Can you think of another possibility to see these tensors? Any idea? I don't see your faces, but I take from the 10, 15 seconds of silence that is not clear anybody has any idea. Well, do remember, please, that a key aspect I've been emphasizing here is that there is a transfer function here. And the transfer function for the modes crossing during radiation domination is a scale invariant, and hence we pick up the original shape of the spectrum, quasi-scale invariant. But what about the transfer function for matter domination? We said that it picks up some scale dependence. So the idea I was hoping one of you would guess is what happens if we think of a period before we reach radiation domination, between the end of inflation and the onset of radiation domination. We don't know the expansion history of the universe that well. We don't know when the matching between inflation and radiation domination took place. We don't know at what energy scale, we don't know when it took place. So it is perfectly possible that there could have been another matter-dominated era or other type of expansion history between the end of inflation and the onset of radiation domination. All we know is that before we reach big bang nucleosynthesis, we need to reach to radiation domination. But when and how, we don't know it. So a very simple speculation is to think that there is some period before reaching radiation domination where the equation of a state is different than radiation. In radiation is 1/3, and this makes this k to the 0, and this is why the transfer function for radiation dominated modes or modes crossing during radiation domination is constant. But the transfer function for modes crossing in with another equation of a state in the background is different. And in particular, if we consider what is called a stiff equation of a state, which is bigger than 1/3 for radiation, but smaller than 1, or up to 1, then this is a rising, a growing function. So one possibility could be if we can rise up this tail, the ultraviolet tail, the high frequency tail of the inflationary background due to a stiff period before the onset of radiation domination. One can do the calculation, and the background now breaks scale invariance, okay? Because the background today now has a high frequency tail, which has an exponent here, a tilt, that is controlled by the equation of a state. And then, of course, there is the height of the background, which is controlled again by the energy scale of inflation. And there is this turnover feature, the change between flat and a tilt background, which is controlled by the moment when we match between whatever period we have. Here I call it a stiff dominated, and then radiation domination. So notice that because I have a rising up spectrum now, a blue tilt spectrum, there is a natural limit as to how much gravitational waves you can tolerate. Because since they are massless degrees of freedom, they behave as radiation. Once they cross the horizon and become propagating gravitational waves, they behave as radiation. And if they behave as radiation, we can only tolerate up to a given amount at the Bbn time. So there is this so-called Bbn limit, which I highlight now with these arrows. And as you see, this background, when we tilt it with the equation of a state, we are gonna violate, for some values of the equation of a state, we may violate the Bbn bound, no? So essentially the Bbn bound, depending of course on the scale of inflation, so what's the height of this spectrum, wants or demands that the equation of a state of a stiff era is as small as possible. Okay, you cannot tolerate the maximum values. White region here is ruled out, and compatibility with Bbn requires the green regions. And the different green colors depends on the Hubble rate I tolerate. So essentially, Bbn compatibility requires, let me call it like that, a small equation of a state, but detectability with LISA, for instance, requires as high as possible, because this is control, this is, how to say, it's monotonically controlling how large is the equation of a state omega, how big is the tilt, and hence how much more observable within LISA, for instance. So within LISA, presumably we could detect a huge parameter space of this background, but the problem is the compatibility with Bbn requires that only the small portion of this space is really compatible for consistency. And if we zoom in into this region, what we discover is that a very small portion region, no, in parameter space, here is equation of a state of the background of the stiff era versus transition frequency between stiff and radiation is very small. Okay, these values are even not motivated by any theory. So this is very unfortunate, because the answer was potentially yes, there is a way to observe inflationary background if there was a stiff era, but consistency with Bbn and CMB actually makes it not very feasible. Okay, so far so good for the irreducible background gravitational waves. I see a question.
There is a question, I think,
yeah,
in the chat.
Yes, the question from Emmanuel is there an assumption here that the stiff era completely fills the epoch between reheating and radiation domination? Yes. Here the assumption I was taking is that actually reheating happens during the stiff era. There are some scenarios which are called geometric preheating and gravitational preheating, various forms of this, where you actually envisage, you engineer a stiff equation of a state, and you reheat thanks to the fact that you have a stiff equation of a state. So the whole reheating is the stiff era in these scenarios. Yeah. Okay, so that's as good as we get for the irreducible background of gravitational waves from inflation. The best hope is really to measure it in the CMB through B-mode experiments. Of course, I would love to stop myself to let you know how that works, but this is really not a course on cosmology, which is what that would correspond to explain those aspects of the CMB. So we are gonna just continue with other gravitational wave sources during inflation. Now, inflation is a very flexible paradigm, and what I was describing so far is the vanilla scenarios of quasi-de Sitter background during inflation. But of course, inflation is flexible enough that admits extra ingredients. For instance, we can invoke extra field species by invoking certain symmetries to play some role during inflation, and this can act as a source, as an extra source of gravitational waves. We can actually, as we will see, enhance the scalar fluctuations, perturbations, and this also helps to enhance the gravitational waves. And then you can enter into a plethora of modifications of standard assumptions, and all of these arguments enhance gravitational waves. Let's have a look to the first example, invoking extra species modulo symmetries. Paradigmatic example of this, what I mean by this is the so-called family of scenarios of axion inflation, which invoke a shift symmetry. So essentially, your Lagrangian is invariant, or the symmetry of your Lagrangian is approximately invariant under constant shifts of your field. Now, of course, in order to inflate, you need to break this symmetry. So you need to consider to some degree the breaking at the potential level of the symmetry, but invoking the symmetry still, you can write these derivative couplings to fermions and to gauge fields. And notice that this is nothing but an axion like a field. This is what we are describing, but this is not the QCD axion. Not even also the axion that can do dark matter, can act as a dark matter candidate. This is a very heavy axion like field, which is good for inflating and for a very interesting phenomenology through these couplings. So these are derivative couplings because given the symmetry, it cannot depend on the amplitude of phi. I leave it up to you, the argument, or you can ask me why this that seemingly is linearly in phi is really a derivative coupling, but it is, okay? Sorry, I have the answer here, I forgot. The reason is because FF dual is a topological term, so it's equal to a total derivative, and then integrating by parts, you can translate this total derivative into a derivative of the scalar field, okay? In any case, the shift symmetry is a very nice property of a system because it protects the potential from radiative corrections, which is interesting because it's a problem there are in other scenarios of inflation. So we are gonna assume a scenario where we have a potential. Sorry, it says curly phi here, it should be normal phi. Okay, the inflaton is a pseudo scalar field, an axion-like field. And we are going to assume that this axion-like field is coupled to FF dual of some gauge sector. For simplicity, I'm going to take an abelian sector. So I'm going to think of a photon-like gauge field, which I can decompose in the usual manner in two helicities. So here I'm summing over helicities, mode functions, and so on, and I'm quantizing this field. And if we study the equation of motion of the gauge field and we decompose it into its helicities, we realize that the dynamics of the two helicities are different. And this is because this is a CP breaking interaction. This is breaking precisely the symmetry between one helicity and the other. And this is manifested in this different sign here for the different helicities, where we have introduced this parameter psi, which depends on the background dynamics, okay? Velocity of the inflaton, Hubble rate, and this F constant that controls the strength of the coupling here. Now, you can solve this equation for the two helicities, and for one of them, for the positive one, since psi typically is negative, it means that the positive sign here gives a tachyonic mass. And if you have a tachyonic mass in an oscillator-like equation, it's not a harmonic oscillator, it's an exponential growing oscillator kind of. It's not even an oscillator. Well, sorry, it is an oscillator, but the amplitude is growing exponentially. Okay, and you can do some analytical approximation to the solution of the unstable mode, which is the positive chirality in this case, whereas the negative chirality would remain almost constant, has no amplification. Okay, so having this kind of coupling is extremely interesting because we are going to excite gauge fields in a non-trivial manner all along inflation. So gauge fields are going to be excited during inflation. They are going to have a given non-trivial spectrum as we go exciting them. And if you compute their energy momentum tensor, you see that there is a non-trivial transverse traceless part, which hence source gravitational waves. So if we follow the dynamics of the tensor modes during inflation, now not only we have quantum fluctuations to start with, we also have a source, which is the transverse traceless part of the electric and magnetic configurations of this gauge field we excite. And since the gauge field is chiral, because only one polarization is excited due to the chiral nature of the coupling, then the gravitational waves are also going to be chiral. We are only going to excite one of the two polarizations. In this case, I'm using the chiral bases left and right hand-sided, okay, which are linear combinations of the plus and cross we saw 2 days ago. Well, I'm not going to show you the details of the calculation because actually it took us quite a number of years to arrive to this picture. But at the end of the day, when you solve the previous equation using different techniques and approximations, the spectrum of gravitational waves today, the omega gravitational wave energy density spectrum versus frequency, it looks like a rising up function. It's not a constant tilt now, okay? It goes up and then it starts smoothing and it will become a plateau at some moment. So the extra fields, the gauge fields we are exciting during inflation are sourcing a blue tilt gravitational wave background, which furthermore is chiral because only one helicity is excited, and furthermore is non-Gaussian because there is a non-vanishing 3-point function that we are not going to show, but it's a characteristic of this background. So what is the most relevant aspect of this picture that I'm showing you here? Well, it's not so much that it's chiral or non-Gaussian. What is really relevant is that, okay, compared to quantum vacuum fluctuations, which is orders of magnitude larger, okay, this was the same quasi-scale invariant background we were seeing before. And what is really relevant is now we are talking about the possibility to detect it by direct detection. For instance, I put LISA here. LISA has the ability to detect this background. In other words, if we measure this background of gravitational waves with LISA, we will be capable of probing properties of the underlying particle physics, which was the chiral coupling between the axion and FF dual of a gauge sector. So from this measurement, actually, one can parameterize the amplitude of the background depending on the Hubble rate, on this psi parameter that depends on the background properties of the inflationary model, and the tilt that depends at every frequency on the different slow roll parameters and this psi parameter. Don't want to enter much in the details, just to let you know that at the end there are a few parameters. You have them under control, and you can quantify what is the ability of LISA to measure the parameter space in certain scenarios. Okay, here psi versus Hubble rate, here psi versus epsilon eta. So essentially, the important message here is not to take home, it's not just the details of this particular background, is to realize that there is really the possibility of measuring gravitational wave backgrounds coming from the early universe that contain information about fundamental interactions. This is just one example, of course, but the message to take home is that an experiment like LISA and actually others like Einstein telescope and other combination of experiments will have access to the parameter space of this background. Now, I was invoking a shift symmetry for this scenario. There is a question. Santiago, I'm going to propose one thing. Let me see if I can finish in the remaining 14 minutes, and then I take your question, okay? Because I would prefer to finish the lecture, otherwise we are a bit tight on time, all right? So let's postpone the question until the very end. I was invoking a shift symmetry, which excites the fields, the photons, in a non-trivial manner. What about I consider an arbitrary type of field coupled to the inflaton without invoking any symmetry? Will I excite in a large manner these fields, and will they create gravitational waves? Okay, same question here. Can I excite fields in a different manner and then correspondingly create extra gravitational waves? Let's consider a scalar field chi coupled to the inflaton through this quadratic manner. The inflaton is phi here. A fermion field through a Yukawa-like interaction to the inflaton. And if you want, instead of thinking of the inflaton, let's think of a spectator field which is charged under some gauge symmetry. And let's couple through the standard covariant derivative the gauge field with this charged scalar field. So under any circumstance, can I excite this scalar chi fermion psi gauge field A mu? Well, yes. Notice that I'm introducing here some scale phi naught, because the effective mass in all the cases, in all the three cases, the effective mass of the scalar fermion and gauge fields is given by the coupling, whatever coupling I'm taking here, okay, I call it G everywhere, times the amplitude of the field, the inflaton, minus some arbitrary phi naught choice I make. When this becomes vanishing, the derivative of the mass is bigger than the mass squared, and this is called a violation of adiabaticity, which translates into a non-adiabatic excitation of the field perturbations. Here I'm writing the occupation number. It's an infrared effect. It only excites in the infrared scales, infrared to this scale mu, which depends on the coupling and the velocity at this point phi naught. So essentially you can choose whatever, you can make a choice of phi naught and some moment in your potential and excite your field like that. This non-adiabatic field excitation in all three cases generates an anisotropic distribution of the created species, in the sense that if I compute the energy momentum tensor, it's non-trivial and has a transverse traceless part in all three cases. So in all three cases, people have worked out what is the relative distortion of the energy of the power spectrum, the total power spectrum, minus the vacuum, the one from vacuum fluctuations normalized by the vacuum. So essentially, visually, how this looks like, don't look at the formula, look at the plot. It corresponds to a bump, a distortion of the quasi-scale invariant background with a given width controlled by this scale mu and a given height. This is the relative distortion, which unfortunately, if you do your computation in every possible case, is much smaller than 1. So this is a negligible distortion of the otherwise scale invariant background. So what we learn here is that, yes, I can invoke the presence of extra species during inflation, but unless I have something very special as a shift symmetry, I do not produce a continuous gravitational wave production. I rather produce a localized production. And in the case of the shift symmetry, actually, we produce a very large background, blue tilt, and potentially observable. In the case of arbitrary couplings, unfortunately, the production is negligible. Well, such is life. What about another possibility? The possibility of enhancing scalar perturbations and see how that back reacts into enhancing gravitational waves, tensor modes. Let's focus on that. So remember, inflation, it's a natural generator of the fluctuations of the scalar, the curvature fluctuations, and the tensor through quantum mechanics. And in a slow roll or quasi-slow roll, we compute it in detail following the actual somehow lengthy computation from quantum mechanics. What's the amplitude of this spectra once the modes become super hard? But this was computed in quasi-slow roll, which is typically the case of monotonic single field scenarios. However, what about if the potential is non-monotonic? Okay, non-monotonic means I change the rate here of the potential, and it's not clear here, but it goes slightly up. So essentially, it's like you have like a small valley or a plateau, and then you are changing all the regular behavior. No, so essentially, your inflaton produces the CMB perturbations when it has an amplitude, remember, for instance, in chaotic inflation, in monomial inflaton potential of the order of 10 of the Planck mass, here I'm not specifying the model, there is some scale of reference. We can think that at high field values, we produce the CMB fluctuations as small as they are, as observed in the CMB. But once we get into this region, close to the end of inflation, the velocity decreases just because the potential is becoming flatter, and then we enhance the scalar fluctuations. Okay, and actually we can really enhance this scalar spectrum at the smaller scales. Okay, it happens later on that we provided the CMB scales from inflation. In multi-field inflationary models, when you have like different directions for the fields, it's also possible to create in the multi-field potential region where the velocity of the main degree of freedom is decreased, and this again enhances the curvature fluctuations. We're not going to enter into those details because again that would be entering into a course on cosmology, on inflationary model building, but please stay with me and assume that these are real possibilities by which I can enhance the amplitude of the scalar fluctuations. These are still quantum scalar fluctuations, but we can enhance them. If we look at the spectrum of fluctuations, of scalar fluctuations in the universe versus a scale, we see that the CMB for few decades, corresponding no more than 7 eFols, those are the 3 decades in multipolar space in the CMB temperature spectrum, they provide a very, very strong constraint on what's the amplitude of the scalar fluctuation. But for shorter scales, higher case, the constraints are much more loose, and in particular, the only constraint we really get is from primordial black holes and very short scales. So let us suppose that our scalar fluctuation spectrum can become much larger than that of the CMB at much smaller scales than those of the CMB. Because the CMB scales are cosmological scales. Let's consider our standard decomposition in a scalar vector tensor, metric perturbations, doing inflation. And now, if we consider that we are enhancing so much the scalar fluctuations, we can work out here second order perturbation theory and see how the bilinear terms actually source non-trivially the linear terms of the tensors. So essentially at second order in perturbation theory, the scalar fluctuations through these gradient combinations, which you don't need to look in detail, of course, all you need is to know is that it's a bilinear combination, provide themselves an effective source for gravitational waves. So if you enhance these scalar fluctuations, you are going to create a new source for gravitational waves. If you do the numbers, although these numbers are a bit out of phase, there's a whole formalism to compute what is the energy density spectrum of the tensors as a function of these guys. Essentially, you can translate now the constraints in omega gravitational waves into constraints in the power spectrum of the scalar fluctuations. Okay, so at Bbn, the Bbn constraint gives us a very poor constraint on the amplitude of scalar fluctuations. But once LISA operates in the 2030s, given the sensitivity, either we detect this background of second order induced scalar fluctuations, or we will place stringent constraints, maybe not as competitive to the CMB, but still stringent at the scales of LISA, which in hertz, in frequency means millihertz, to the amplitude of the power spectrum of the fluctuations. For pulsar timing arrays, which are the experiments nowadays, which I mentioned yesterday in the session of questions that they could be at the verge on discovery of a gravitational wave background, they will put also very nice constraints. Actually, it's better than this, but unfortunately, I'm using an old transparency here from 2010. There is a much better number here. So it's still a very good constraint on the amplitude of this power spectrum scalar fluctuation at those scales. Or maybe there is a detection, which will point out to the fact that there is a mechanism in inflation that really enhances scalar fluctuations at the scales corresponding to PTA experiments. And in the future, if a futuristic proposal called Big Bang Observatory gets ever built, this could really reach much better sensitivity in omega gravitational waves, and it could put even a much better constraint or detection on the amplitude of scalar perturbations. Now, if I enhance very much the scalar perturbations, as I was also explaining in the set of questions yesterday, this can lead to the production of primordial black holes. This happens when these scalar fluctuations that are very large, they cross inside the Hubble radius during post-inflationary cosmic evolution, and because they represent such a big fluctuation, they collapse the whole Hubble patch where that happens and produce what is called a primordial black hole during the radiation-dominated background history of the universe. So primordial black holes actually are a candidate for dark matter, yes, but only in a very specific range. So if you want to explain dark matter with primordial black holes, this is possible, and you need to arrange your inflationary potential such that it creates black holes large scalar fluctuations in a given moment in the inflationary expansion, which corresponds to the scales that once they enter the Hubble radius in the post-inflationary expansion history will give rise to these mass scales. Okay? You can cook your inflationary potential to do that very easily. If the PBHs, primordial black holes, are the dark matter, actually there is, the possibility to measure this gravitational wave background to second order with LISA. It happens to be in the same window, okay? They actually are is a non-Gaussian background, although it's very difficult to measure this non-Gaussianity. And people are starting to work out other properties like the anisotropies of this background, okay? So it's very interesting that we are characterizing the background in different manners, such that if we eventually make a detection of a background, we have other observables beyond the power spectrum to try to differentiate this background. Now, $1 million question is, has LIGO, Virgo, detected primordial black holes? No, it's detected already, like of the order of 50-ish pairs of black holes. Are these primordial? Well, we will only know by building the statistics of the mass spin distribution of them. And the latest analysis, to my knowledge, of what the data tell us is not good enough to differentiate whether there is a subfraction of these black holes we are detecting being primordial. Okay, so as of now, this remains as a question that is not answered. Okay, and let me check how I'm doing on time. Okay, I'm 30 seconds before we arrive into 45 minutes second part. So essentially what we've seen is that you can invoke extra species, and if there is a nice symmetry, like a shift symmetry, you can very much enhance the gravitational waves above the otherwise very small quasi-scale invariant quantum fluctuation background. You can also enhance it through the enhancement of scalar perturbations. And then, of course, there is the possibility of other modification, like modification of gravity, or having spectator fields or other aspects. These also contribute to enhance the gravitational wave background, but we don't have time for everything. We just arrive at 45 minutes. So I leave you with a reference I think this is my review, but maybe it's another review we did on inflation. In both of them, you have information about these other aspects. And we live with the perspective here now, we stop with the perspective that tomorrow we will start dealing with the reheating of the universe. And we conclude the inflationary part here. Okay? Although reheating is a fundamental part of the inflationary framework, it's just what happens after inflation. Okay, so this is it. I think there was a question before. I'm happy to take it now if you want.
Yeah, I forgot who he was, but
yeah, me too. Sorry.
He can just pick up.
Okay, can you speak up? Maybe Santiago is better if you unmute your mic and you ask out loud the question.
Yeah, exactly.
So my doubt is that you said that if we assume an extra symmetry, like shift symmetry, we can enhance the creation of a particular polarization of gravitational waves. And my question was whether that polarization is what then creates also mode B polarization in the CMB, and if that can constrain how much we can deviate from CPT symmetry.
Interesting. No, what creates a B mode in the CMB has nothing to do with the polarization of the tensor, has to do with having a tensor in first place, okay, or a vector for that matter, except that the vector perturbations are vanishing, okay? So, of course, in the CMB, there are searches for these CP violating kind of couplings, parity violating couplings, okay? But precisely because this background, if you look, let me go back a little bit. If you look at the shape of this background I was discussing, you see this is a blue tilt background. Look, here is where it comes. Okay, let's look at it in this plot. This is a blue tilt background, which rises up above the otherwise quantum fluctuation background, which would be a scaling variant. Now, inflationary scales are here on the left, on the plot, are not inside the plot, okay? So because this background grows like that, I cannot sustain this growth of amplitude at the CMB scales here at the low frequencies. So in order to validate this, to have this background like this, I have to satisfy a number of constraints at the CMB scales. And this tells me that the CMB scales, this background is dominated by the quantum vacuum fluctuations. Whereas fulfilling those constraints, nothing prevents me from having here in dashed blue line the contribution from this induced source, the chiral photons, which overtakes around this frequency in this particular computation, it overtakes the quantum vacuum fluctuation. But in the CMB, this is not going to happen because it would violate many constraints. For instance, non-Gaussianity constraints. Okay? Since the source of these tensor modes are the gauge fields also contribute to scalar fluctuations. They are non-Gaussian, and there are limits of the non-Gaussianity at the CMB scales. And these are constraints we need to take into account.
So it's something from high frequencies rather than what one would expect from the CMB.
Correct. Here we are talking precisely about direct detection of gravitational wave backgrounds at high frequencies from the point of view of CMB. At high frequencies is the normal frequencies for us in the detectors. It's just the CMB is low frequency because it's a cosmological probe. It's probing cosmological wavelengths, hence extremely small frequencies. But any experiment we do is going to be probing much higher frequencies. And that's interesting. That's beneficial for us because it means we can work out our inflationary setups such that they all make the same prediction for CMB fluctuations. They respect CMB fluctuations, but at shorter scales, so later than 60 folds before the end of inflation, they do something fancy to enhance scalar and tensor fluctuation, which is compatible with cosmology and potentially detectable with this kind of observations.
Okay, thank you very much.
My pleasure. Any other question?